Hello everyone, this is Raju, my CA assessment 2 in second semester. Today my topic is about direct and indirect band gap semiconductors in engineering physics. Let us go to our topic, direct and indirect band gap semiconductor. Our topic contents are introduction, band gap basics, direct band semiconductor, indirect band semiconductor, applications of direct band semiconductor, applications of indirect band semiconductors, band gap engineering, compression of direct and indirect band gap semiconductor, band gap transition of semiconductor, future trends in band gap semiconductor reach, challenges in band gap semiconductor development, and conclusion. Let us go to the first introduction. Semiconductors play a crucial role in electronic devices. Band gap is a key parameter in deciding the semiconductor. There are two types of band gap, direct and indirect. First one, band gap basic. The band gap basic is energy difference between the valency band and the conduction band. Indirect band gap semiconductor, the minimum energy of the conduct band allocation with the maximum energy of valency band. In indirect band gap semiconductor, the minimum energy of conduction band does not allow the maximum energy of valency band. Direct band gap semiconductor. Direct band gap semiconductor have high absorption efficiency, electron and hole recombine energy easily. Indirect band gap semiconductor. Example of direct band gap semiconductor include gas and input. Indirect band gap semiconductors. Indirect band gap semiconductors have low light absorption efficiency compared to direct band gap semiconductor. Electrons and hole have different monomia in direct bandgap semiconductor make recombination less efficient. Example of direct bandgap semiconductor include Si and Ge. You can see the picture how it direct band gap semiconductor works. This one is direct band gap and indirect band gap semiconductor. And let us go to the another slide. Applications of direct band gap semiconductors. Direct bandgap semiconductors are commonly used in optoelectronic devices like LEDs and laser. These semiconductors are preferred for applications requiring efficiency light emission. Direct bandgap materials are crucial for the solar cells due to their high absorption efficiency. You can see the picture how it semiconductor applications works like conductor band gap, Fermi energy, valency band, metal semiconductor insulation, increasing energy, overall lab. And another slide. Applications of indirect bandgap semiconductor. Indirect bandgap semiconductor are widely used in electronic devices like transistors and diodes. The semiconductors are efficiency applications requiring electrical conductivity. Indirect bandgap materials find applications in internal circuits and microprocessor. Same direct semiconductor and indirect semiconductor pictures are similar. We can see the previous slide same also. Bandgap energy. Bandgap energy involves modifying the band structure of semiconductor to tailor their properties. Direct bandgap materials can be energized by specific wavelength emission of optoelectronic devices. Indirect bandgap materials can engineered for the improved charge carries modify electronic applications. Compression direct in the indirect bandgap semiconductor. Direct bandgap semiconductors have higher recognition rate compared to direct bandgap semiconductors. Indirect bandgap semiconductors have longer carry time left times due to the lower recombination rates. The choice between the direct and indirect bandgap materials depends on the specific applications required. Let us go to the another slide. Bandgap semiconductors in transistor. Some semiconductors can exhibit both direct and indirect bandgap properties depending on the crucial structure. Bandgap transistors can occur under certain conditions impacting the semiconductor's optical and electronic properties. Understanding bandgap transistor is essential for optimizing semiconductors performing in direct applications. Let us go to the another slide. Features trends in bandgap semiconductor research. Ongoing research aims to enhance the efficiency of both direct and indirect bandgap semiconductors. Novel materials and fabrication techniques are the explore to improve the performance of semiconductor devices. Bandgap energy continues to be a key focus area for developing next generation electronics band optoelectronic technologies. You can see this picture how it works, condition band and valency band. This gap is band gap, and this is energy and insulator. Insulator is zero energy high. Same same this is condition. This is band gap semiconductor B, and condenser condition band gap is overlap. You can see the difference of the semi insulator band insulator semiconductor and also combination. Let us go to the another slide. Challenges in bandgap semiconductor development. Overcoming materials limitations, the enhancing bandgap control or the ongoing challenges in semiconductor research. Achieving high quality direct bandgap materials with tailored properties remains a complex task. Balancing the trade-off between light emission efficiency and charge carries mobility in semiconductor design poses challenges for the device optimization. Let us go to the another slide. And last one is conclusion. Direct and indirect bandgap semiconductors offer distinct advantages and are crucial for the various electronic and optoelectronic applications. Bandgap energies plays a visual role in customizing semiconductor properties for the specific requirement. Continued research and development in a bandgap semiconductor technological or essential for driving involving in the semiconductor industries. And thank you.